teacher. Today we are going to look at another topic under thermodynamics, and that is the first law of thermodynamics. The first law of thermodynamics. First law of thermodynamics. Thermodynamics. Alright, that is what we are going to be looking at today, the first law of thermodynamics. But before we begin with what we understand by the first law of thermodynamics, it's important for us to let us know that as part of your contribution to these classes we are doing online, we just need you to go to our YouTube channel and subscribe. And very importantly, do not forget to share. Share it with your friends, with your colleagues, fellow students, so they can subscribe and also be part of these classes. You can leave your comments also at the comment section. They'll be attended to, even if there are questions. Go to our Facebook page and follow Dr. B chemistry classes. Also share with your friends and colleagues, and also like and comment. All right, believing that you have done that already, now let us quickly understand what first law of thermodynamics means. It's important for us to know that thermodynamics itself, that thermodynamics is divided into classical thermodynamics, okay, and then you also have the quantum thermodynamics. Okay, so this can also be called the statistical thermodynamics. Okay, so thermodynamics itself is divided into classical thermodynamics and quantum or statistical thermodynamics. And the classical thermodynamics deals with the macroscopic, deal with the macroscopic parameters, while this deals with the microscopic parameters. All right, and then these microscopic parameters are like the electrons, okay, the neutrons, okay, those very minute particles, okay, while the macroscopic deals basically with particles like with systems rather, that borders on temperature, borders on pressure, borders on volume, okay, borders on enthalpy, borders on entropy, also borders on the Gibbs free energy, etc. So you can see that classical mechanics talks more about these very major parameters that are built on large scale discussion, large scale measurements, while the statistical thermodynamics deals with microscopic particles that deals with very minute scale discussion like neutrons, like electrons, okay, and a whole lot of them, protons and all those things. Now, this classical thermodynamics deals with the first law, deals with the second law, and the third law of thermodynamics. That is where we find the first law of thermodynamics. It is under the classical thermodynamics, and everything you'll be talking about is the first law, second law, and the third laws of thermodynamics. And these laws borders on enthalpy, borders on entropy, and then the Gibbs free energy. Okay, so this is where our topic, first law of thermodynamics, fall under classical thermodynamics. Now, it is important for us to know that the quantum or the statistical thermodynamics discuss three basic laws, and that is discuss laws like Fermi-Dirac, okay, the Fermi-Dirac statistics, okay, the Michael Boston, okay, Michael Boston statistics is discussed under that, okay, and a whole lot of them. So we have about three basic statistics that are discussed under the quantum or statistical mechanics, and one of them is the Fermi-Dirac, okay, and the Boston statistics, and then you have the other ones. But we will not bother ourselves with the statistical thermodynamics. We are concerned today with the classical thermodynamics, and under the classical thermodynamics, we're talking about the first law of thermodynamics. The first law of thermodynamics. Now, it is important for us to also know that when we are talking about the first law of thermodynamics, there is need for us to ask ourselves a particular question, that how do we come to terms with what first law of thermodynamics talks about? Now, do you know that when you put a kettle with water inside it and put it on top of a gas that has a flame, and then after some time you will notice that the water will start steaming, and after the steaming you will start seeing vapor coming out of the water? What have you just done? Some kettles will even give you a kind of a whistle sound at the end of the day. What have you just done? You have shown technically evidence of the first law of thermodynamics. So we do it every day. You want to boil water to take your bath? You put water in a kettle and put on the flame. Before you know, cold water turns to hot water. Before you know, it starts boiling and vapor is coming out. You hear your kettle with some sound showing that water is boiling. That is evidence of the first law of thermodynamics. And what have you just done there? What you have done there is this. You have decided to supply the kettle that contains that water with heat. And then you have also decided to raise the internal energy of the system, which is the kettle with the water. You have raised the internal energy by the supply of the heat. And eventually, work is done. The work that is done is what you are seeing in the vapor that is leaving, and also in the whistle sound of the kettle. Did you see how simple it is? And that is everything about the first law of thermodynamics. So the first law of thermodynamics is built on three parameters. It's built on internal energy is built on heat, is built on work done. These are the three parameters that define the first law of thermodynamics. Remember that the first law of thermodynamics is the same as the law of conservation of energy. Okay, so whenever you think of the first law of thermodynamics, think of what? The law of conservation of energy, which says that what? Energy cannot be created nor destroyed, but it can be transformed from one form to what? The other. That is the law of conservation of energy, and that is the definition of the first law of thermodynamics. That is the proposition of that particular law. Energy cannot be created or destroyed, but can be transformed from one form to the other. Now, what is the implication of this particular law that we just stated? What do we mean when we say energy cannot be created and can be destroyed, but can be transformed? What do we mean by that? Now, what we mean is simple. Once heat is supplied to a system, the internal energy of that system will vary. And once there is a variation in the internal energy of the system, then work will be done. So the heat that is supplied to the system in the form of energy will not be wasted, will not go off. Now that work is done, any amount of heat that is left will be transformed to another type of what? Energy that will also produce work after all. That's what it simply means. So when we look at the first law of thermodynamics, we could just simply say that internal energy of a system depends on heat supplied and work done. So that means heat supplied to a system and work done are the function of internal energy. So one can simply say internal energy is equal to the function of what? Of Q and W. That's what it means. It means that the heat supplied and the work done are the function of internal energy. That is to say, once heat is supplied to the system, internal energy will be affected and work will be done. So wherever heat is not supplied to the system, the internal energy remains constant. And we don't expect work to be done in a system. That is just what it means technically. So I want us to know that when we talk of first law of thermodynamics, we are talking about the interconversion or interrelationship of heat, work, and energy. And it borders on the fact that internal energy of a system will change, either increasing or decreasing, if heat is supplied to that system, and eventually work will be done. Now, if that is true, let us take a look at something here. Do you know that work can be negative or work done can be positive? Yes, in any system at all, work done can be positive or negative. If you are cooking, you are boiling water, work done can be positive or negative. If you are eating food, work done can be negative or positive in your body. If you are running, the same thing. And work done can be negative if the work is done by the system on the environment. As we are standing here right now, I'm talking to us. Is it not so? And perhaps where I'm standing is hot, and I am assimilating heat into my body. The work that is done allows me to sweat, and by sweating, I'm contributing to the environment. Therefore, the work done is going to be negative because the internal energy in me is reduced, and it is favoring rather the environment. If the internal energy is reduced by the way I am spending energy, my internal energy is being reduced, then it means that much of the energy is leaving me into the environment. In that way, the work done is rather favoring the environment. Therefore, work done is negative for the system and positive for the environment. But where the environment is rather contributing heat to the system, it means that work done is done on the system by the environment. Therefore, the system is gaining more internal energy. So it's favored. Heat is what? Heat is actually coming into the system and increasing internal energy of the system. So work done is what? Positive on the system. Now, this is what we mean. This is what we mean. Now, supposing we have this. Supposing we have this. This is a piston. And this is our system. Alright. And then we have this. And these are gas molecules. Okay. Okay, let's extend the piston to this point. Okay. And then we have another one. We have another one. Okay. And then here, we rather have here. And this is the piston. And now here we are having this. Do you notice that what we have here is compression? What we have here is compression. And what we have here is expansion. That's what we have. This is the piston. This is the piston. Okay? So, what we have here means that there is a gas that was perhaps at this particular level. And now the piston is used to press the gas. So it compresses the gas. And as it compresses the gas, what happens? There is increase in pressure and there is a reduction in volume. What does that imply? What it implies is that there is supply of energy. Okay, this is the internal energy is supplied to it. So at this particular level, where you rather have the system being compressed, it means that work is done. Work is done by the work is done on the system by the environment. These gas molecules here are being compressed. As they are being compressed, it means that the system is benefiting from what? The internal energy. So it gains more internal energy, and because it gains more internal energy, work is done on the system by the environment. That's what it means. So if we say so, it means that our internal energy will be equal to Q plus W. Of course, where this is the infinite heat, infinite internal energy, this is the infinite heat supplied, and this is the work done. So in this kind of a situation, it means that work is done on the gas, okay, by the environment. By the environment. That's what it means. Because here it means that the system is gaining more internal energy. Therefore, work is done on the system by the environment. In that case, we have a positive work done. But if you take a look at what you have here, you will see that here there is negative pressure and positive volume. That is to say, there is an expansion here. As you pull out the piston, pressure is reduced, negative pressure, and what? And volume is what? Increased. In that case, heat is rather leaving this particular system to what? The environment. And if it does that way, it means that the internal energy of this kind of a system is reduced. Therefore, you have a negative work done, because work is done by the system on the environment. So in this one, we say work is done by the system on the environment. You see, therefore, it means that our internal energy will be equal to Q minus W. Take a look at this. Did you see that when work is done on the system by the environment, there will be increase in internal energy. Therefore, work done is positive. But where work is done by the system rather on the environment, the system will lose internal energy. The environment will gain. Therefore, work done becomes negative. These are the major things we need to know. Because everything around first law of thermodynamics is built on heat, energy, and work. That interplay is what is very important and vital in thermodynamics. Now, if we assume that we have this basic understanding of what that means, then the equation for first law of thermodynamics is what we have written here. So this equation and this equation, whether you use positive or negative while writing it, it is still the same. It is the equation for the first law of thermodynamics. That is to say, for the first law of thermodynamics, the mathematical representation is du equals to dq plus dw. Some will tell you change in u equals to change in q plus change in w. It is the same thing. Why this simply defines the infinite internal energy of the system, this q defines an infinite heat change, and this defines work done by the system. And we have explained when work done by the system is positive and when it is also negative. Now there is something that is interesting. When we say work done, what do we actually mean by thermodynamic work? Because we're saying work done, work done, work done, work done. What do we actually mean when we say thermodynamic works? What do we mean by that? Thermodynamic work. It can also be called mechanical work. But what do we mean by that? Do you know that thermodynamic work, which we are talking about, work done, work done, work done, is simply that energy that is converted from one form to the other. that is what we mean by thermodynamic works. That is thermodynamic works for you, mechanical work. That energy that is converted from one form to the other is simply what we call thermodynamic works. And we can possibly derive it. Yes, we can derive it. Now let us derive it. Let us derive thermodynamic work. If we agree that thermodynamic work is simply that energy that is converted from one form to the other. How do we arrive at that thermodynamic works? So let us see how we can be able to derive thermodynamic work, okay, which is work done, and is given as W. But we start that with something. Assuming we have a compression. We have a compression here. Okay, and this is a piston that is dropped here. Like we did before, and these are gas molecules, usually ideal gas. Okay, gas molecules. Now, this is the piston. Okay, this is gas molecules. This is the surrounding. Okay, the whole of this is the surrounding, and then from here to here is the X. That is the distance covered by what? The gas, which is compressed. And then remember that here you will have always a negative pressure and also a positive volume, because as the gas is being compressed and also relaxing, okay, it's being expanded and also compressed, you have negative pressure and then you have volume. And then the whole of this particular area where you have the gas stain is what you call your surface area. Your surface area, and is given as A. Now, if we have these parameters that describe the distance covered by the gas, the pressure of the gas, the volume of the gas that will always change as well, and the surface area, how do we now determine thermodynamic works? Now, let us look at it. I want us to first understand the fact that there is a force, okay, exerted by the piston. Know that this piston is going up and coming down. Therefore, as it's coming down, it's exerting a force. In thermodynamics, the force that is being exerted by the piston is simply the surface area multiplied by what? Multiplied by the pressure. Okay, that is minus P. The surface area multiplied by the pressure defines that force exerted by what? By the piston. And then the volume change is also defined by the surface area times the distance covered by the gas. Of course, you know that volume has to do now with the surface area and the distance covered by what? Covered by the gas in the container. Now, the work done, change in work done itself can always be defined as the force times what? Times the distance. And here, this is the force and this is the distance. That means to look for the distance, we have to do some conversion. So, but distance from equation 2 will be equals to dv all over A. That is what you have here from equation 2. Distance, so the formula dv over A. We have this. Okay. They will give us equation 4 because this is equation 3. Now, if we have this, that means that we can now do what? We can now substitute equation 4 and equation 1 into what? Equation 3. We can now substitute this equation and this equation for force and for distance. So if we are going to do that, this is how it's going to look like. If we are going to do that, then we are going to have the W. We have the W is equals to force, which is minus PA multiplied by this, equation 4, the X, which is distance, and this will give us the V over A. That's what we have. Of course, this A will cancel this A, so the W will be equals to minus P dV. Okay, so this is 4, 5, and 6. Now, when we get here, you can simply substitute this to the normal thermodynamic equation, first law, which I had already pointed out. But here we can integrate. We can integrate with respect to what? V. The V, change in V. So we have that W is equals, because this is change in W, we are looking for only W, which is the work done. So the work done therefore becomes minus to the integral of V2, V1. We are integrating with respect to what? Change in volume, and that is from V2 to V1, initial, a final and initial. So this is P dV. P dV. This dV can be rewritten. So we can have W equals to minus, okay, P V2 minus V1. Of course, you know that this is the same thing as change in V. Now, if we choose to introduce our first law of thermodynamic equation, okay, from first law equation, you have that change in U, which is the internal energy, is equals to what? Q plus W. Now this is our W. So we now have that change in internal energy U is equals to Q minus, because this minus crosses this, so minus P V2 minus V1. Now this is the definition of work done in the thermodynamic equation. But work done as it is defined by this equation here. So thermodynamic work is defined by equation 7. Thermodynamic work is defined by equation 7. To understand whether the work that is done is on the system or by the system, you put it into the thermodynamic first law equation. And here you can understand that this particular equation shows you that work is done by the system on the environment. So there is a negative work done. I'm sure that we have learned something interesting today out of thermodynamics. Just take your time to sit down and watch gradually. This is quite a very shorter version of you deriving the thermodynamic work, which is simply the energy that is converted from one form to another. Now, do not forget to subscribe. Do not also forget to comment. Don't forget to share. Most importantly, share with your colleagues to be part of this beautiful thing we are doing online. Share with your colleagues. Tell them to also subscribe to get these videos once they are being dropped. Go to our YouTube, our Facebook page, and also follow. Share as well to your colleagues. Comment and like. Until next time, it is bye for now.